At the table live from the Western Conference. Keith Payet, Jay Wilson, um, Kirk Klinghorn, Dan Lane, Rich Russell, and myself, Dave Westman, which is good for this kind of situation. And we're going to hear Vikram Ravi give us a speech on the viewing the view of the radio sky at this point. So this is our keynote speech for the Western Conference. Glad to see you here this morning.
Everyone for joining. Thanks for joining online and thanks for coming all the way out here. I know it's a long way to travel, and we're glad to have you visit, and glad the weather's cooperated as well. We're between as you know, a couple of storms, and it's going to rain again next week, and it rained this week, and also happens to be very good for my visit up here, where we're actually using those 2mm dishes out there right now. The sort of two pointing in the same direction, which you would hope they are, because we're using them as an interferometer at the moment. So, well, let's get started. So I'd like to tell you a bit about some of the projects that we're working on to really change the way that we look at the radio sky. So I'll tell you in particular about projects that use antennas for those online, like those pictured here, and for those locally, you can see them out the window. The idea is that we're really moving from these sort of systems of a few or maybe one large bespoke antennas and receivers, all the way to antennas and receivers that can be relatively mass-produced and deployed in ever-increasing numbers. And there are various benefits of this, which I'm sure you can appreciate. So, this is the given the audience, you certainly know why radio astronomy is interesting, but I thought I'd just remind us all why we're so fascinated by the radio sky. So to begin with, this is an image of the a position about half a degree away from the galactic center in infrared. When you look at the sky like so, of course, one highlights all sorts of interesting things that one otherwise doesn't see. In particular, what I really want to highlight in this image is all the high energy processes that are really invisible at other wavelengths. For example, there are remnants of supernovae that exploded somewhere between 1,000 and 10,000 years ago. There is a very young pulsar over here, and pulsars, of course, have a relatively strong wind of relativistic particles. But because the pulsar is moving through this dense medium, the wind sort of shows up as this trail behind it. You have these sort of active galactic nuclei, AGN, so these distant supermassive black holes. And then you have unexplained things like these non-thermal filaments, which remain a mystery. How do we have such coherent, large-scale magnetic fields that can confine the relativistic particles that are radiating? I'm going to try and animate this while playing. If I do this, you should be able to see the animation there. This is an image in neutral hydrogen of a relatively nearby face-on spiral galaxy. And what you see when you look at it in the comparison between the optical and the hydrogen gas is that you see this much larger extent of the gas around the stellar disk. And the gas really does not trace the stars very well. Maybe it does in these outskirts here, where you might see evidence of this spiral arm in stars, but the gas really tells you a different story about this galaxy from what you're seeing in the stellar distribution. So we really care about radio astronomy scientifically because we see the universe in ways that cannot otherwise be seen. What we want to do is, of course, see the sky a bit better. And so the way that we're trying to do this is by really leveraging various advances in the way we can build antennas. And so, first of all, digital signal processing hardware and stream computing developed for many other applications are being leveraged to radio astronomy. And on your tour today, you'll see examples of that. For example, downstairs, we have 24 servers, each hosting a relatively powerful graphics processing unit, each of which can deliver 14 teraflops. Sure. Yeah. So each delivers 14 teraflops of computing. And so there's a lot's happening under our feet as well as around the site. The other things, of course, are that we can now sample gigahertz bandwidths directly, right? We can sample gigahertz bandwidths, and so we don't really need to down convert when we're at gigahertz wavelengths. The other one, which is sort of a relatively unexpected advance, is that we can actually get receivers that perform as well as the best cryogenic receivers at gigahertz frequencies. And so this array over here, which participants in the room will see in person, consists of many of these small antennas. Currently about 70 are deployed. Each of them has a system temperature of 25 Kelvin without a cold receiver. Morgan Cather's entered the room, and I'd like to thank Morgan for this video.
What's that?
I'd like to thank Morgan for
Oh,
yes, for having made that. I'd like to tell you today about the DSA program, the Deep Synoptic Array. This is a rather what's the word? Heterogeneous collection of experiments and antennas. Many of you will know Sandy Weinreb, pictured here in the in 2013 in the DSA-1 telescope. This was used as a prototype for a larger antenna, larger array, but that didn't end up being built. Instead, when I arrived at Caltech in 2015, we started building this DSA-10 array, none of the antennas of which are upright on site anymore, some of which are being used as covers for various holes in the ground and so on. You may see them on your tour. But this was really groundbreaking for us in the way that it introduced us to these sort of larger arrays of very small antennas and what they can do. That made some interesting discoveries. It led also to this array over here, which doesn't look like an array at all because it looks like a feed. We actually just deployed 3 of these feeds pointing up at 3 locations across the southwest of the US and used it to discover a fast radio burst from within the Milky Way. So these were literally the receivers from the tops of these antennas pointed up. The receivers there, you can sort of see one pictured faintly over here, were sourced from a ham radio operator in the UK, and were at the time the best LNAs we could buy at L-band without cryogenic cooling. We thought we could do better, and so Sandy and his group developed receivers for the DSA-110, which now reduces system temperature by about 40 Kelvin relative to DSA-10. We're then, in the future, working on something called TRACK, which will be an array of 960 antennas, a phased array in a very small patch on the ground that should see most of the visible sky at once, as well as the DSA-2000, which I'll spend some time talking about, which really we see as the future of radio astronomy in these frequencies. So most of these arrays and antennas, however, were designed for one purpose, which is fast radio burst science. The DSA-2000 is designed for a whole variety of scientific outcomes, which I'll describe. So let me introduce fast radio bursts. I'm going to try and play this animation, although we're not in the presentation mode. There is no FRB here, but there will be in a second. But what the data that we sort of search for these in are, of course, spectra, typically at L-band or maybe a bit below, and high time resolution. I think there's a talk a little later on FRB science as well. So what this looks like in real time is this. Let me play it again. I'll just repeat it a few times. We're searching for these swept frequency signals that basically tell us that the bursts are coming from quite a large distance. So the idea is that we can take the amount of sweep in the burst and attribute this to an intervening plasma column and use that to estimate the distance to the burst using sort of assumptions about the density of the burst. And we find that these things are coming from very large distances, gigaparsecs in some sense. Right. Are there any questions online? I see many things in the chat. No? Good. Okay, we're okay. We care about FRBs for two main reasons. One is that we don't know what emits them. We have ideas, mainly centered on neutron stars, in particular the most extreme neutron stars we know about, but we don't know how they form, we don't know what happens to them, how long they live for, we don't know what they do to their environments, we don't know what they tell us about the endpoints of stellar evolution. We also don't know what physics emits such energetic radio bursts. A single burst carries about the same energy as the sun outputs in about 100 years, just in radio waves, just in a millisecond. The physics underlying that is just not known. The other thing that's really interesting about FRBs, and I'm going to play this video through, is that we can use the propagation of the bursts to tell us about intervening matter. So the amount of dispersion tells us the total column density, and by observing the amount of dispersion in different bursts, we can associate it with different intervening structures along the line of sight. For example, the DSA 110, the array out here, has discovered the first two FRBs from large galaxy clusters. And so we're able to actually measure the amount of matter within these clusters in an entirely different way to which we were able to do before. And this is sort of a fundamental problem for astronomy today. How do galaxies form out of and influence the matter around them? So what do we do? Let me see. I'm not sure how to play this. I am going to try one more time to get the presentation mode working, just because I'd like to try and show some of these photos. Let me just try to hit play again. What I'm going to do is I'm just going to try resharing I really do want to try and show these photos. And so let's do this. Yes, this works. Good. The DSA 10 was the very first array that we tried to build. And it was an interesting time for the observatory because we'd just gone through a transition after the Karma telescope was shut down. The millimeter dishes were brought back to the valley floor, and the observatory was really being sustained by the CO map, a CO intensity mapping program, as well as DSA 10 at the time. And so DSA 10 was a departure from what the observatory done before, these sort of really precise, carefully built antennas and receivers to $1,700 antennas sourced from Alibaba.com. And you get one as pictured here, shipped, 10 of them were shipped in a container from China. 1,700 including shipping, amazingly enough. Just 4.5 meters across. We assembled them with the help of Katie Hudson in the shop at the other side of site. Sandy and his group designed the feeds and the back-end electronics. This is our really sophisticated range test of the feed. We were really on a shoestring for this. Please. Indeed, yeah. Sorry, the question for those in line was, is this all at neutral hydrogen frequency? Yes, we were operating between 1280 and 1530 megahertz. So we put out 10 antennas. You can see the configuration here and the interferometric sort of PSF in the top left. Here are 4 antennas pictured. This is at the north end of this T-shaped infrastructure. They're no longer there. They look kind of nice. $1,700. I mean, they don't steer at all. They're fixed. You have to take a large wrench to them to move them. We made some aftermarket modifications. Exactly. That's right. And amazingly enough, this discovered a fast radio burst from a distance of 8 billion light years. I mean, the light was traveling for 8 billion years before it hit these tiny little dishes. And you can see a movie of the burst in the middle there, as well as the sort of light curve of the burst up here and its spectrum. The burst itself lasted a fraction of a millisecond, about half a millisecond, and we were able to associate it using interferometry with this galaxy at redshift of 0.66. It's truly amazing that something so tiny could see something from so far away. And this made us really excited and got us going to the next array, the DSA 110. This is an NSF-funded program at the level of about $6.2 million. The idea is to put out about 95 antennas on the core of the array, so this T-shaped infrastructure in the middle, as well as 15 outrigger antennas to provide the localization. The antennas were a bit more sophisticated in this case. We sourced them not from China, but from Wisconsin. They were spin formed in one piece and then cut, and the panels were delivered to site. And on your tour, you may see some of them over the other side of the site. Bit more, someone took more people to install them, and we were a lot more careful in how we got the form. In a minute, you'll see, let's see if I fast forward a little bit, you'll see our sophisticated jig to get the form right. One innovation we made to these is we installed fiberglass feed support legs. And we found a particular fiberglass that was as transparent to radio emission as we could. And then you'll see later on the feeds are mounted. This thing is just sort of tipped on this little jig and taken out to a trailer and brought to site. Infrastructure-wise, the idea was to distribute them as far across this 2.25 kilometer site as we could. We trenched along the boundary of the site. It was the summer of 2021, which was a very hot summer. People trenched during the heat of the day. Largely, it was a heroic effort. I mean, just yeah. For those on the tour, you'll see the outriggers sort of spread all the way across the site. We have these antenna boxes where we have a custom interface board for monitoring control, as well as the LabJack microcontroller. 486 fibers were terminated in a vault underneath where I'm speaking from. The team spent a few months in this room splicing fibers. It was I don't know how it's done. The receivers were one of the real sort of innovations that enabled this array to have the performance it does. The feeds, one thing I want to highlight about these feeds is that the 2 rings on the outside, the choke rings, are actual cake pans from a company called Fat Daddy-O's, which is heavily featured on the Food Network. And they have the right properties, right size, and so on. They're very robust. And so here's one of the feeds in the antenna, and the low noise amplifier delivers typically less than 7 Kelvin noise temperature at ambient temperature. And this a couple of the innovations that enable that. One was the use of a very high speed, so a 200 gigahertz transistor, as well as a very carefully designed input matching network to try and get rid of any possible impedance mismatches. We sacrificed half a Kelvin by using silver-plated N-type connectors rather than gold-plated N-type connectors to the feed. But it's half a Kelvin at 25. That was okay. What's interesting is that the input matching network was basically done by sort of leaving this central conductor exposed on the substrate. but then building a sort of a waveguide out of the metal casing in which the LNA cards were placed. And so sort of these were built during COVID. In fact, all of DSA 110 construction was during the COVID pandemic. The LNA assembly involved the chassis being built in a shop in Tunisia, where the cousin of one of our engineers had a shop in his garage. And so they were built in Tunisia, shipped to Sandy Weinreb's house in Pasadena. The transistors come from a company in Switzerland. It's a two-person company. The CEO and president is also on the shop floor. And they were also shipped. Sandy inspected them, sent them along to another person who had the pick and place equipment. They then walked to another person's house to test, walked back to Sandy, who then walked to the post office to mail them up to Overo. All contactless, all during COVID, and they were built. So what does it actually do? So this is a relatively realistic depiction of the area on sky, the square in the top left, that the DSA observes at any given time. It's about the size of 40 full moons. We need to pinpoint FRBs within that to somewhat better than 1 part in 10 million. And so that's what the optical image of a region that size might look like. And then we need to figure out the FRB location to the size of that little circle. This is a real localization that we've delivered to, yes, about 1 part in 10 million of the original field of view. And so in 22, this array has delivered 30 FRB discoveries, which more than doubles the previous number that had been published. These are specifically those FRBs that are localized to small enough regions in the sky that we can find host galaxies. So we're not just saying we've seen the burst, we're saying that we know where they come from. One thing sort of that's fun about this is that I've ordered them by increasing estimated distance to the burst, all the way from a distance of about 50 megaparsec to a distance of over 10 gigaparsec. And the ones in the bottom right, in at least this optical data, do not have evident host galaxies because they're very faint. When we observe with the Keck telescopes in Hawaii, we do indeed see host galaxies there. Whereas the ones in the top left have somewhat larger and brighter host galaxies, typically. For this audience, I thought it'd be fun to show some polarization data because I just think it's really interesting. So what you see here is a de-dispersed pulse profile. The units on the x-axis are milliseconds, and we're seeing the 4 different Stokes parameters, I, Q, U, and V, as well as the position angle of the polarization vector at the top. The structure is amazing. You can see Stokes Q, U, and V flip. Sure, yeah, it's sort of appearing and disappearing. Here we go. I've got a mouse. Yeah, it's sort of appearing, disappearing from my screen. You know what I mean? Yeah, I don't know why. Yes, maybe if yeah, it's very, I don't understand it. In any case, we have a mouse here, and I think this is actually a better view of the same data, which projects the polarization state onto the Poincare sphere. So one axis is Q, one axis U, and one axis is V. And as the burst evolves, you can see 2 distinct polarization states of the burst. And I mean, the amount of structure is truly amazing. And we don't have any idea what causes it, but theorists have interesting thoughts. Yes.
Is it with the top plot on the last slide, Jim?
The top on the last slide, up the top here, shows the angle between Stokes Q and U as a function of time. Yes. Yes, that's right. So I feed the polarized feeds, and we measure all the polarization states. Yes. So with that, I'd like to move right ahead to the DSA 2000. to tell you about where we're going next. Looks like I've got plenty of time. Great. So the DSA 2000 is something that the team is working very hard on at the moment. So I'm just going to do this for, there we go. Yeah, so the team's working very hard on at the moment, and this is what we believe will be the future of radio astronomy at these frequencies. So many of you will have heard, for example, of the square kilometer array, the SKA. This has the same sensitivity while delivering somewhat over 6 times the survey speed of the SKA. This array is currently in a design phase, and we anticipate starting construction next year in a valley in Nevada. And so really, we're very excited about what this can deliver. And it's really based on the heritage of the DSA 110, the DSA 10, the DSA 1 program. The antennas are very similar. The receivers are very similar, just a wideband version of exactly the same DSA 110 receivers, but everything else is different, as I'll go through now. So first of all, just to set the scene, radio interferometers are telescopes that deliver images, right? Fundamentally, we are very what's the word? We're very we like to use radio interferometers a lot because they're able to deliver images without many of the systematics that single dish telescopes are subject to. And the reason is that we directly measure the spatial coherence function of the incident radiation. And we measure it in a way that is not susceptible, for example, to gain variations in individual antennas. As the idea is that the interferometric measurements can be transformed into the image plane. We observe the Fourier transform of the image. And so the idea is that we go from interferometer arrays like the VLA on the left, that has a particular point spread function. And so when you observe the sky, you see the sky convolved with that point spread function. So this is what we call a dirty image. And then after a lot of effort, you might get the image on the right, which we call a clean image. The process of going from a dirty to a clean image is really difficult. It involves modeling the sky, modeling the point spread function, and calibrating the array all at once. So why do we want 2000 antennas? Well, this is what an image of a very simple sky, a uniform disk, might look like with just 30 antennas. As this disk looks like what it does on the left. So the VLA has 27 antennas. This gives you an idea of, what that uniform disk might look like with an array that size. It looks like a disk. It looks disk-ish, right, on the right. You can sort of say, I can reconstruct that. But what if you have a more complicated image? So this is an animation now of what happens as we construct a more complicated image, not a disk, but something with much more structure, as we step up the number of antennas. So as we go to 50, 100, 150, maybe you can start to see things appear now. This is my my thesis advisor in front of the Parkes telescope. You can see that the artifacts slowly start to disappear. And when you get to the 2000, it looks really good, right? You're not only recovering you're basically recovering it in an artifactless way. In fact, the artifacts when you have 2000 antennas are typically 1 part in 10 to the 5 of a given image. So you can sort of see when you get to 2000 antennas, the fidelity of the image reconstruction is so good that we don't have to do any cleaning at all.
Are they randomly stacked?
Yes, they are. In this simulation, they are, in fact, the baseline distribution was constrained to be a Gaussian.
So this kind of proves that the artifacts come from the gaps in the array that you experience when you have a low number of arrays, basically, that you have to fill in and sort of do heuristic assumptions to get your data. And with the high number of arrays, you don't have to do that any longer, and you actually have good data in almost every possible place that you really need it. And
that's right.
Causes a really good clean image.
That's right.
That's where it comes from. Right.
Yeah,
Sure.
absolutely. And so arrays like the VLA use aperture synthesis to fill in some of the gaps. And so they'll observe for a very long time, so the projected baseline distribution will shift.
Right.
They also use frequency synthesis. So the baseline, the effective lengths are different at different frequencies. And so you can interpolate your image that way. We don't want to do either in some sense, because we don't have to do it. That's right. Yes. And so because we want to survey the sky fast, we want to spend as little time in a given field as possible. Because we want to also survey the sky in H1 for neutral hydrogen, we don't want to have to do frequency synthesis if we don't have to. So that's why 2000 antennas. So the idea is that this is a radio survey telescope designed to survey the sky, but not just in radio waves. We're also, as it turns out, a gravitational wave survey telescope, because there is a technique where by timing pulsars around the sky, you're able to detect the influence of gravitational waves in the arrival times of the pulsar pulses. And so we want to do this with an array of 200 pulsars and look for very small variations, typically at the tens of nanosecond level, to actually discover very low frequency gravitational waves. So that's what we call it, multi-messenger survey engine as well, where it's an array that doesn't just do radio astronomy, it uses multiple messengers to study the sky. And so the idea is 2,000 5-meter dishes. The artist's impression is shown here on the right. We want to place them in Hot Creek Valley in Nevada. It's about 3 and a bit hours drive northeast of here. We cover 0.7 to 2 gigahertz with a spatial resolution of 3.3 arc seconds at the middle of the band. We expect to have first light in 2026 and commence surveys in 2027. When you compare it to current or future arrays, the DSA 2000 in the space of the survey speed versus sensitivity really excels on the survey speed axis while having competitive sensitivity as well. We will survey the entire sky north of declination -30 to 500 nanojansky RMS across the whole sky. This will yield somewhat over 1 billion radio sources, most of which will be star-forming galaxies throughout cosmic history. About 1 in 10 will be AGN, and the rest will be a smattering of unknown objects we expect. Something over 4 million galaxies detected in neutral hydrogen, as well as 10 to the 5 FRBs and pulsars. And the two technologies that enable this are the radio camera digital backend, which I'll describe, as well as this the cryo-free antenna and receiver based off the DSA 110. What does this look like? So again, we're sort of using a cake pan style feed, now working with Fat Daddios to have them machine 2 cake pans into, give us what is effectively 2 cake pans, like a bundt cake tray for the feed. And we're also extending the LNA to perform over the wider band using the same transistors we have experience with. Our simulated performance posits a TSIS under 20 Kelvin at zenith, with all contributions included. And of course, it's a bit worse at the bottom of the band, but we're very optimistic that we'll deliver this based on current prototyping. We anticipate doing various key surveys. Most of the time will be spent on this cadenced all sky survey, so 16 epochs spaced by 4 months of the whole sky north of -30 declination. 25% of time on this nanograv project, which is the gravitational wave detection, and then some follow-up of LIGO discovered sources, as well as some deep fields. Our confusion limit is about 50 nanojansky. So the limit where background sources are blended into each other is at the 50 nanojansky level. And so we can reach that in just about an hour on a given field. The radio camera is something that is probably the new aspect of this. If we were to store visibilities like current interferometric arrays do, we produce 20 exabytes of data every year, which we cannot do. There is no chance. And so What we want to do is make use of the fact that our images have high fidelity to just store images. And so on the top here, we see a simulation of a dirty image on the top right, made with the VLA, and the same field with calibration errors included of from the DSA 2000 on the bottom right. And you can see that basically you have science-ready images with artifacts below what we would get, even if we worked really hard with the VLA, without doing any cleaning. There are some rare cases where you have roughly 1/10,000th of the sky, where you have really bright sources in your field. So where you have, say, a few Jansky or above sources, these do need to be cleaned in the image plane. And so we basically divide out the PSF in the image plane, knowing the locations of these sources. And so the idea is that we do the whole thing in one go. We do the cross-correlation, flagging, calibration, gridding, and imaging, and then deliver images directly without ever seeing the visibilities. We anticipate about something like 5,000 NVIDIA GPUs deployed for this at the cost of, 12.5 million just for the computing. The rest of it is relatively inexpensive. This will yield a public archive of under a petabyte, as well as 50 petabytes of imaging data. And this is perfectly feasible with data storage today. And so our timeline is ambitious. We are in the stage where we're basically doing the preliminary design at the moment. We have a science meeting at the start of next week down in Pasadena. And this will culminate in a preliminary design review later this year, as well as a full proposal to the NSF. Our funding model is a public-private thing. We're going to go to the NSF for just over a third. We will go to our current funder, which is the Schmidt Futures. Hopefully for a third. We'll put a proposal in. This is Eric Schmidt's philanthropy. And we would go to a partner, an international partner, for a third as well. The total cost for construction is, yes, about 144 million, and then operations is at the level of 6-ish million per year. And yes, our meeting is scheduled for next week. And so with that, I think I'm done. Happy to take many questions. We are deploying these ever larger arrays of small antennas to really change the way that we see the gigahertz radio sky. The DSA 110 is our currently nearly complete iteration of this, which is really changing the way we see fast radio bursts. And the DSA 2000 is something that we're very excited about and will be a key activity of this observatory in coming years. Thank you.
Thank you very much, Vikram.
Thanks.
Could you say what size staff you're anticipating for DSA 2000?
Yeah, that's a really good question. So construction, we're hoping to contract out almost everything. So we're working with commercial partners on antenna construction, on fiber and power layout, on and everything we possibly can. In terms of operations, Morgan's probably thought, honestly, more about it than I have.
Well, there's one big piece of construction. So
At the moment, yes, that's right. Yeah.
the plan.
Yeah.
Major reflectors ourselves to it.
Yeah.
A hydroinflation process that we would do in-house for the reflectors themselves.
But then in terms of operations, we intend to have a staff on site all the time, working in pairs. So probably 6 operations staff and probably another 6 to 10 maintenance staff as well. With 2,000 antennas, it takes the mean time between visits to an antenna gets extended to a few years. And so we're hoping to visit every antenna somewhere between once every 2 to 3 years. When we need a mean time between failure, ideally we're designing for 20 years for everything.
Is this one reason why the United States did not participate in SKA?
Not quite. The question was, the line is one reason why the US did not participate in SKA. That decision was made about 13 years ago. Whereas this concept really came up in 2018 or so. But I think you could look at it in this way, which is that the reason why the US decided to pull out of SKA was that the so-called decadal survey in astronomy in 2010 reviewed the SKA costs that were being projected and found them to be nearly a factor of 2 higher than what astronomers were saying, which is, there's a long history of astronomers doing this. But it was, the feeling was that it was too expensive for the science return. So this is about a 20th the cost of the SKA. Yeah.
Is there any opportunity for citizen science participants in this project? Yeah, I see you're going to get a huge amount of data here.
Yeah.
And there's a lot of exciting stuff out there. The sky is very full of all sorts of interesting things. And I can see that you could make use of all sorts of amateur brains to help work with this project. And we'd like to see a piece of that.
Yeah, so citizen science opportunities will be, we're very excited about that because so one of the programs that we're hoping to do is do a very large pulsar survey. But to do that, we need to identify candidate pulsars in the images first. Mm-hmm. And so this requires matching with multi-wavelength data and basically saying which radio sources don't look like galaxies, which radio sources don't look like AGN, which ones don't look like stars or H2 regions or anything else, and then find the ones that look like pulsars, points not really associated with much, maybe a faint star. And so this can be done in an automated sense, but there will of course be too many candidates for us. And that's one citizen science opportunity we've identifying the best candidate pulsars. Others, for example, there is this radio galaxy zoo, which some people here online have heard of. That's something we could easily extend into this.
Yeah, I can see that. You know that SARA has already been working on pulsars quite a bit. Mm-hmm. And we have our telescope out in Haswell, Colorado, which we use for that kind of search. And also our German friends, Wolfgang Hermann, who's going to give a talk later on this morning, has working with a telescope in southwestern Germany, which also does much the same kind of thing and a lot of other things too. Yeah, it's a very good, nice telescope.
Indeed,
for an amateur, it's a fantastic telescope.
Yeah, I believe that's the Stocker, telescope. Yes, right. Yeah,
that's a great telescope.
Yeah, it really is.
Consequently, we're already trying to do things in this field for an amateur level, and I think that being participants and helping you work in this project would be great.
Yeah, that would be amazing. Absolutely. Yeah.
We have an online question from Bob, who is asking, it's a 3-part question. What ambient temperature range are you designing for?
Great question. So we are designing for the extremes of the weather at Hot Creek Valley. So somewhere between -10 and +45 Celsius. The LNAs themselves are typically tested between +50 and -50 Celsius. That's an interesting thing because we actually see a decrease in the noise temperature just in that range. Not even before you get to cryogenic temperatures, we see a decrease, and that the physics underlying that is not known. We recently submitted a proposal to the NSF with an applied physics professor at Caltech to try and explain this, because if we can explain it, we can hopefully apply it. The other aspects are the dish, the reflector surfaces themselves. We're looking at thermal expansion and so on, and we are going to incorporate some solar avoidance to avoid extra heating. Yeah, I think that probably covers it.
Okay. You also asked, what is the anticipated wind speed protection?
So that's an important one for the dish and the dish and the mounts in particular, where it's folded in both into the lifetime as well as the power requirements. So the idea is that we will stow at a relatively modest, something like 10 meters per second. And we have weather data that suggests that will affect us sort of a few-ish % of the time. And so we're planning to really cap the power draw for a given antenna, as well as cap the requirements to maintain pointing accuracy in high wind in order to make the engineering a bit easier, but also reduce the cost of the turning heads. We are planning sort of solid dishes, no holes in them. So it really just is a big sail. The other thing there is that the pointing accuracy requirements are and the dish surface accuracy requirements are very stringent. So despite the beam being about 3.5 degrees in the middle of the band, we want sub arc minute pointing. And this is because we need that in order to minimize systematics in the camera approach to imaging. And so we don't want primary beam errors, sort of which get inflated when you have pointing errors to actually affect the images on large scales. So we have a stringent pointing requirement. The dish surfaces are being designed to be lambda over 200, not lambda over 20. Again, to minimize errors. And so we want to maintain that in whatever gravity as well as wind.
Polarization, we've always had a debate about single or dual polarization and then combining them.
Yeah.
How are you guys doing that?
Yeah, so the it's an evolution of DSA 10 and 110. We have two linearly polarized probes within the waveguide. And so we sense the X and Y polarizations, and then we do the correlation between them to get the circular. Yeah.
So your show is 2000 relatively compact.
Yeah.
First off, what's the diameter of that? And then secondly, what about throwing a few outliers around? Give you a semi very large baseline.
Yeah, this is a really good question. So the question was, what's the diameter of the DSA 2000 configuration, and could we have outriggers? The configuration is 19 by 15 kilometers. We've got we're leaving open the possibility of outriggers, but we're not building that into the baseline design, mainly because it takes time to acquire land. That's the main thing. So we're leaving it open for now, but our baseline is just to have a single array. We will have voltage beams available for VLBI specifically.
Did you mention the brand of that dish on the left there?
No, I did not. Anderson, I believe.
Affordable perfection.
Affordable perfection? Wow. Wow.
Where'd you find that?
Where we find the dish?
I mean, the vendor for that.
I don't know. This was before my time.
This was Anderson. Anderson hydroforming. Yeah.
Oh wait, really?
Yeah.
That's
Okay.
the Wisconsin guy.
I thought
No.
the brand was Affordable Perfection.
I think the brand was in the end, but the dish itself, the surface itself, was made by Anderson.
Oh, okay.
Yeah. This is not the Wisconsin guys. These are hydroformed, and the Wisconsin guys spin formed with mandrel sort of forced against. Yeah.
Radio technology, wow.
Yeah. Morgan.
On an earlier slide, you mentioned that one of the assumptions was 80% uptime for the array. Is there a similar assumption being made about number of signal paths online?
Sure. So the question was, given that we're assuming an 80% uptime for the array, is there an assumption about the number of signal paths online? Yes. The number that we've typically quoted for the number of online signal paths is n minus 50 or so, where n is probably 2048. Given so we say DSA 2000, the configuration currently has 2048 antennas. We anticipate about 2000 online at once.
They can make it 2048 for FFT.
So the question was, do we make it 2048 for FFT purposes? No. That we just Dave Woody, who some people know, has been leading the configuration work and likes the number. I think there's no more to it than that. Yeah. Just a nice power too. Yeah.
See it in FFT.
Indeed.
Time, that's why.
Yes. Yeah.
Another online question, what impact do you anticipate from weather and particularly sandstorms?
That's a great question.
Can you,
Yeah.
in other words, he was saying, can you collect through that or will you need to shut down?
So, in the context in sandstorms in particular, I'd expect the wind speed to be so high that we would shut down. Rain is something that will affect us to some extent at the high end of the band. The troposphere does contribute a bit to phase errors at 2 gigahertz. But same token, space weather contributes to phase errors at 700 megahertz, and so that we're also cognizant of that. We do anticipate in the worst case scenarios the effects of weather that don't cause shutdown are all in phase errors, really, right? So the worst errors are those that are common to subsets of the array. So for example, imagine a cloud over one portion of the array that the rest of the array does not see. Those are the most insidious because they're the hardest to deal with in the image plane. And so we're using techniques developed for the VLA in its extended A configuration to mitigate these. So that's probably the worst case scenarios when you have storms coming through that we want to try and observe through, but which cause these phase errors.
I'll let you read the question.
Sure thing.
We're down to here.
I see. Thanks.
Wolfgang.
Great. So Wolfgang Herman asks, what will be the F to D ratio of dishes and what consideration determine the choice? About 0.31, I think, close to 0.31. And the main considerations there are, one, our particular feed design is well matched to this. We are slightly under illuminating to minimize spillover. We're also hoping by use of these shields on the edge of the dishes to minimize spillover even further, but also crosstalk between antennas. And so the low F to D ratio means the feed is sort of relatively deep in the dish. Otherwise, no, that's it. Those are the two main considerations. It's a joint optimization between the feed and the antenna design, given the prime focus configuration. So the next question is, are there any problems with wildlife being interested in the antennas? Yes, very much so. And not just wildlife, but people. Because we're not planning to fence off the 19 by 15 kilometers at all. We're planning to just have these antennas in isolated locations. The mean separation is a few hundred meters. It's not, the mean separation between antennas is not as close as it appears in some of these images, that it's about 300 meters. So we're debating if and what sort of fencing to put around each antenna. Either chain link fencing, chain link fencing is probably the way we'll go at the moment. There is grazing, so cows definitely will be interested in antennas there, as they are here. The polarization states of the long wavelength array antennas here have been modified by the cows, shall we say. The pointing of DSA 10 antennas is modified by cows, you know, sort of rubbing themselves up against them and moving them across in azimuth. But no, so it is something we need to consider. But at the same time, we need to also consider protected wildlife that wants to migrate through the valleys. And so we need to be careful not to sort of erect too many barriers to that as well. So. What about the rednecks shooting at it? Great question. We've been advised to be to expect that by the local BLM office, and we haven't got a strong mitigation yet. On site here, there is a shooting range off to the edge of the site, which is good. We also have signs that I don't know why we put them up. It's sort of talking about, you know, no admittance except for authorized personnel, which are great targets as well. So you know, if maybe a few of those signs would help. But yes, it's something we need to think carefully about. Yeah, because it's hunting grounds. It's
It'd be great if you can make some of these guys partners in your efforts so they see the value in it and you know, begin to really cooperate with you on this, because we don't need hostility when it comes to science.
Yeah. So it's actually it's an interesting question locally there, where it's not necessarily locals where we're concerned. I mean, I'm not just concerned, we're working with locals.
Yeah.
But it's more people coming in from elsewhere who want to hunt in the valley that we're advised to be careful of.
Right, sure.
So that's a new thing for us, because that's not something we face here. So there's another question online that just came up. Can we get access to your feed design details? The manufacturing of the fiberglass rods would be good to know. I can certainly provide the fiberglass rod details relatively quickly, and the feed design, I suspect so as well, because certainly for the DSA 110, we can do that pretty quickly. Yes. Yep. These should. Trying to think, I don't think Sandy put it in his instrument in his LNA paper. No, it would be we'd have to do it separately. Yeah, but yes, we can.
So are you anticipating any serious challenges, radio frequency interference from LEO satellites?
Great question. So RFI from LEO satellites is probably the worst source for us, but it also is the one we can control and understand the most. We know where the satellites are, we know where they radiate, and so we can choose our survey strategy to avoid them. It's the Starlink type of things that get a bit harder because you can't avoid them, but they are instructed now by the government to not transmit into that valley, just like they're instructed not to transmit here. And so we're able to control newly launched satellites, especially telecommunication satellites, from transmitting within these valleys. And that communication's that loop's been closed. Our worst RFI problems are really the things we don't know. So any future developments in the valley, future access to spectrum, we don't anticipate now. And so we're designing to be as robust as possible to RFI.